Still on Chapter 8, but we're going to change. Instead of a yes-no question, now the data is going to be a how much, how many question. This is the difference between counting and measuring. So in this case, we're measuring. This is going to make a couple of changes. First, with the yes-no questions, it was a proportion we were interested in. So for the null hypothesis, we had P equals. Now, since it's a how much, how many, we're looking for a population mean. And so it's now mu equals for your null hypothesis. There's another distinction that you have to be aware of, and that is that we have to use different distributions depending on whether sigma is known or whether sigma is unknown. Your calculator will do most of the work, but you need to make this decision on your own. You have to take a look and, based off of how the standard deviation is talked about, decide whether it's sigma or S. In my first example, suppose that I have a single sentence which says that a group of 8 subjects had a mean of 72.9 and a standard deviation of 12.51. Now, all of that is information about the sample, so this would have been S. On the other hand, suppose that I said that a population has a known standard deviation of 12.51. A sample of size 8 had a mean of 72.9. I've actually done 2 things to indicate that the standard deviation is sigma and not S. First, I've moved it out of the sentence which described the sample, and second, I've included a keyword, something like historically known, generally accepted, or it can even just be called a population standard deviation. Suppose that I went with the first option for this one. Suppose that I said that the sample of size 8 had a mean of 72.9 and a standard deviation of 12.51. Then this would be S. Because it's S and not sigma, we would do a t-test. Next, about the claim, you're going to have to look for a keyword. Suppose that in the first case the keyword was less than. You believe that the mean is less than 74.7. Well, that's a pretty clear example. This would now be a less than sign. Note that I've set alpha to something different from our default. Alpha is now set to 0.01. With all of this taken care of and correctly labeled, we can bring out the calculator. Stat, test, t-test is line 2. You check and see whether the input is coming from raw data or summary statistics. In this case, it's summary statistics. Mu naught is the hypothesized mean. That would be 74.7. X bar is the sample mean. That was 72.9. So it is smaller, but is it small by enough to convince everybody that this is really a smaller number, that this is really from a population whose mean is smaller than 74.7? S is going to be 12.51. Such a large standard deviation means that I'm less likely to be able to reject, especially given that I have such a small number of individuals. I only have 8 individuals. As for which of these to use, because it's a less than sign here, I highlight and select less than, and I'm ready to calculate. Because it was a t-test, my test statistic is t. I still want 3 decimal places, so negative 0.407. Now in this case, p is going to be 0.35. Now that's larger than the 0.01, so this is an example where I would fail to reject the null hypothesis. Next example. Suppose that the keyword is not correct. You believe that the statement that the mean is 10 is not a correct statement. You haven't indicated a direction. You don't know whether you should shoot higher or lower, so the inequality is just going to be not equal to. You take a look at where the standard deviation is described. Suppose that in this case it's said to be a historically known value, and it's given in a sentence outside of the sentence describing the sample size and the mean. If that's the case, if it's historically known, then it's population standard deviation and not sample standard deviation, and so we have a z-test. Our test statistic is going to be a z. When I plug in the numbers, stat, test, z-test, that's the very first line. My input is going to be summary statistics. The hypothesized mean was 10. The standard deviation, the sigma, 0.04. My apologies. Stat, test, z-test. X bar was 9.7. N was 44. So I have a smaller standard deviation. I have a much larger sample size. The inequality is going to be not equal to, and I can calculate. Now the z-score is going to be negative 49.749. This is an incredibly large in magnitude z-score. So large that the claim is that the probability is 0. Technically it's not 0, but apparently it's less than 1 times 10 to the negative 99. It's that small. So p is equal to, I will write down 0. That is less than, well, I didn't specify an alpha. If I don't specify what alpha is, use the default value. Use the value alpha is 0.05. But 0 is less than 0.05, therefore I would reject the null hypothesis. I'm sometimes uncomfortable writing 0 because it's slightly more than 0. I'm more comfortable writing 0 plus, which tells me that it's slightly more than 0. It's on the positive side of 0. But so close to 0 that we can call it 0. Last example. Suppose that the claim is that the mean is 17. Now, you happen to believe that that number, the 17, is too low. If 17 is too low, that means that the true mean, you believe, is greater than 17. Now, here I've just given a bunch of measurements. Suppose that that is all I am given. I'm not given n. I'm not given a standard deviation. I'm just given the raw data. But from the raw data, I can compute x bar. I can just count to get n. And if I'm not given a different standard deviation, I can find the standard deviation of the sample. So that's what we'll do. That will be S. Now, given that this is S, my test statistic is going to be a T, and we're ready to compute. First, we go stat and edit because we're going to be putting in raw data. So you type in 12 and 13 and 16 and 18 and 19 and 19 and 20 and 24 and 29. Note that the next would be the 10th number. Let's just do a quick check. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's right. N is equal to 9. I can now go stat test, and this is going to be a t-test because sigma is unknown. I switch and ask for raw data. My hypothesized mean is 17. The list I used was list 1, so I changed that back to list 1. The inequality that I used was a greater than, so I highlight and select greater than. Now when I calculate, notice that it gives me a lot of interesting information. It does give me P. P is 0.16. It does give me T. T is 1.078. Since I didn't give an alpha, we will assume that alpha is 0.05. 0.16 is greater than 0.05, therefore we fail to reject the null hypothesis. Now I'm done over here, but I was given summary statistics, and since I'm given summary statistics, I can fill in over here. X bar, 18.8 repeating, I'll call that 18.9. One extra decimal place. S, I often give 1 or 2 extra decimal places. I'll give 2 this time. It would be 5.25. And that is how you handle simple hypothesis tests involving claims of a single group of data where the data is a how much, how many type of data.